Thank you for your interest in attending my keynote address that I've titled Philosophy of Science and Science Education, Synergistic Opportunities for Public Outreach. I'd like to begin by telling you a little bit about my background. I earned a undergraduate degree in biology and immediately went to graduate school, earning a Master's of Arts in Teaching and Science Education and completing a significant amount of graduate work in biochemistry, including some, but not a great deal of laboratory work. I then went and taught biology, chemistry, and physics for 1 year in Illinois, actually serving as the department chair my first year as well. And then I, after only 1 year, returned to the university and began a doctoral program in science education. That doctoral program was different than most students who choose to earn a PhD in science education, in that I foregrounded the history and philosophy of science in my studies. Most individuals, of course, in addition to science education, foreground a science content area, but I again chose history and philosophy of science. After finishing the coursework and not yet completing the dissertation, I returned to teaching high school, 6 years in Wisconsin, biology and chemistry. I completed my dissertation 4 years later while I was still teaching high school and continued teaching 2 years longer. I very much enjoy working with secondary school students. I bring this up because the things I'm going to talk about today, a number of them not only reflect my scholarship in the history and philosophy of science, but also my experience working with secondary school students. I always like to tell my students that I did these things with my kids. I know the history and philosophy of science can be taught well both to secondary school students and in outreach efforts. And this is reflected in the past 25 years as a science teacher educator. I have focused on the history and nature of science in science education efforts, again, both at the secondary school level and also in outreach efforts. I work with prospective and experienced science teachers, not only with history and philosophy of science, but also helping them understand how to teach science more effectively. Let me begin by talking about what is referred to in science education as the nature of science. You won't see oftentimes people talk about directly the history and philosophy of science sometimes, but oftentimes they talk about the nature of science. And that phrase is common because we're really trying to capture not only what we know from the philosophy of science, but also what we know from the history of science and the sociology of science. And we address in science education matters such as what you see here: what science is, how science works, epistemological and ontological issues in science, and how scientists interact with the public, how their work interacts with the public, how they impact one another. That's not an exhaustive list, but it gives you an idea of what we mean by nature of science. And of course, these issues are central to the philosophy of science. For some time, well over a century actually, and in some ways even much further back than that, there have been calls for science education to more accurately address what science is and how scientific knowledge is developed and comes to be accepted. And yet, accurate and effective nature of science instruction is quite uncommon. There's a variety of reasons for that I'll return to later, but I want to begin that this is a real problem in trying to get teachers to attend to accurate and effective NOS instruction. Not surprisingly, because of that, NOS misconceptions are quite prevalent. They're not just prevalent among the public, they are quite prevalent among science teachers and even science teacher educators. And again, not surprisingly, they're also common among the public and policymakers. And this makes sense because they arise from the way that science is oftentimes taught. If you think about your science learning experiences, how the textbooks spoke about science, how they didn't address the history of science and how we know what we know, or if they tried to do it, it was quite sanitized. And then you think about common laboratory experiences. We all took part in what we refer to as cookbook laboratory experiences, where you're told precisely what to do, what data to collect. It all looks so very neat and logical. And then you think about the laboratory reports that we oftentimes have students submit to us as science teachers. If you think about it, it fits very well a sanitized view of science. It fits what is referred to as a step-by-step scientific method. Think about teachers' language. things that teachers say, such as this proves this, or this is the truth. They'll use the word scientific theory and scientific law, and they don't use those in an appropriate context. And there's other things they say about science and scientists that convey images about what science is, how it works. And of course, then there's popular media. We know all about that and how that can distort how science works. And we have to realize in our educative efforts, whether it be in schools or in outreach, that many NOS misconceptions simply make sense. They're intuitive notions about how knowledge is developed and accepted. And not only do they make sense, these misconceptions cohere together, which strengthens people's resolve in those misconceptions. And I'll illustrate that. So here are some pervasive NOS misconceptions. The research is quite clear about this. Again, the notion of a scientific method, a unique step-by-step method. And again, many of you probably recall being required to learn that step-by-step method in your school science. Then there's the way that school science promotes the idea and people accept that robust data essentially tells scientists what nature is like. It determines scientific ideas, as if data and ideas, that the connection was not only pretty straightforward, but again, the data tells scientists what to think. This is a common misconception. The notion that good scientists, if they are good in doing what they're supposed to be doing, they're totally objective, not permitting any prior thinking or external factors to influence their work. There is this notion of a sanitized view of science, a misunderstanding of the process of science in the making. When ideas, or I should say when data appears not to fit, it's oftentimes thought by people that this demands rejection of the scientific idea, or at least the idea's re-examination. People wrongly understand or think about the discovery aspect of science. It's much like trying to find something and we find it, there it is. There's the structure of DNA. We've been looking for that. You'd be surprised how many students think that we actually determine the structure of DNA because we got better microscopes and we can see it now. That's overemphasized by people, and the inventive character of science is misunderstood. There's also misunderstandings regarding the similarities, differences, and relationships between science and technology. And this is important because it results in a disregard for basic science research and its funding. We all know that technoscience is perhaps a better phrase for science, indicating how much interaction there is between basic science, applied science, technology, engineering, math. But the public really doesn't understand these differences at all, and they are puzzled by science that is done just to understand the natural world. Many of you might remember William Proxmire and the Golden Fleece Award, Senator Proxmire from Wisconsin a number of decades ago, and that award oftentimes went to basic science. There's also a misconception of a bifurcation of scientific knowledge. It's either seen as true or uncertain, and if it's uncertain, it's unreliable. And then the warfare thesis between science and religion is too often adopted. And all of these interfere with what we want to achieve with science education efforts and public understanding of science. These misconceptions play a role in rejecting science as a possible career. When I was teaching high school, early in any course I would teach, students would say things like, I don't want to major in science, I'd rather do something creative. That's just a very anecdotal example of how these perceptions of science can deter students from thinking it's a career they might want to consider. They oftentimes see scientists as lonely workers in a lab. They don't envision work outside of a lab. And so in our efforts to prepare people to think about science as a career, more accurately addressing the nature of science is important. These misconceptions create difficulties in learning science content and developing robust understanding of counterintuitive concepts. Take, for example, pendulum motion. If we really want students to deeply understand pendulum motion, they should understand that the idea was not developed by looking at how pendulums behave in the natural world. As if any physics person knows, Galileo said looking at the natural world is just going to screw you up. You have to take a mathematical approach. And he, of course, put forward how pendula would behave, how they should behave, if it wasn't for these confounding factors of gravity and friction. And of course, there's that bob that is really problematic. And so he put forth point mass, no string. It was mathematical. And not surprisingly, Galileo's contemporaries were puzzled by that because they were trying to explain the world they saw, and he appeared to be putting forth ideas for a world that should be. But we know why that our current idea of pendulum motion is accepted. But students, I recall a research study where a student who earned an A in physics was said, they teach us that an object in motion will go on forever. And anybody knows that's not true. You can look at it. Objects stop in the real world. Again, understanding the history and nature of science can help students understand how these ideas were developed, why we adopt a law like pendulum motion that really you observe nowhere in the known universe, and yet it applies everywhere in the known universe. There's the unnecessary conflict between science and religion. Any biology teacher like myself knows this comes up when you're teaching about biological evolution. Gnostic misconceptions play a role in the distrust of science. We certainly saw that with the COVID pandemic. And therefore, we have ill-informed socio-scientific decisions. A great deal of research in science education is addressing socio-scientific decision-making, and Gnostic understanding plays a role. Not the only role, but it plays a role. So when we think about effectively conveying the nature of science, be it in school settings or in outreach, I want to address what research is making very clear about effective Gnostic instruction. First, it's planned for. It just doesn't happen by chance. It overtly draws attention to the value of Gnostic learning. It overtly draws learners' attention to the Gnostic idea or issue that you're targeting, and it does so in a manner that engages students in thinking about that issue and developing more accurate understanding. And it occurs in a variety of contexts with extensive scaffolding. And I'm going to go in more detail with each of these. I want to start with it's planned for. It's not merely by chance. It seems to make sense, but research shows that it doesn't work, that little is learned about the nature of science by merely placing individuals in science research experiences. Research has been done where teachers have been placed in laboratories for an entire summer, and it really does not affect their Gnostic understanding unless those other things I'm going to get to are done at the same time. Merely having students read accurate information about the Gnostic doesn't really change their understanding. And merely presenting information regarding how science works doesn't change conceptions. And this is because one of the fundamental ideas that we know is the case about learning is we all, not just our students, but we as well, we use our already existing knowledge, that which we think is the case. We use that in trying to make sense of whatever stimuli is coming our way. So when an educator is trying to help others understand the nature of science, and you might have them read an article, or you might tell them something, they are interpreting that incoming information using their misconceptions. And the research is quite clear that without some of the other things I'm going to talk about, the learner misconstrues, alters the accurate information they're getting to fit what they already think. They're not being belligerent necessarily. They are, again, we have no choice. We understand things based on what we already understand. So what does effective Gnostic planning and instruction entail? Well, again, it overtly draws attention to how accurate Gnostic understanding does a number of positive things for us. We need to bring people in our outreach efforts. We need to bring them in and help them understand what they're going to get out of this better understanding. And they'll make more informed socio-scientific decisions, combating pervasive science misinformation and disinformation. A colleague and I recently received rapid NSF funding to develop COVID-19 materials to address this. And we also have a project that we're going to begin addressing other ways to help people understand the nature of science and how it applies to socio-scientific decision-making. Again, it assists in improving students' learning in science courses. I've mentioned this before, but again, when working with my students or working with outreach efforts, I address ideas, science content ideas that I know are oftentimes misunderstood. And I help those who I'm working with understand how understanding the Gnostic can assist in making more sense of science. Getting back to the attitudes and interest in science, it also helps us as science educators. And our outreach efforts, are working with students understand why individuals have difficulty learning science and the tenacity of science misconceptions and why simply showing and telling are insufficient. If you go back to the example with Galileo, you can imagine him trying to tell his contemporaries, well, you see how this works. And if the world was like this, and you go back and you look at Galileo's contemporaries, very bright individuals, and their response was, I don't know what you're doing, Galileo, because we're trying to explain how the world works, and you're seemingly dealing with a world that can't exist. If that's the case with very bright people in the past, and of course this applies throughout the history of science, where ideas have had to be altered, it certainly is going to apply to our outreach efforts and working with students in our classes. There's nothing intuitively obvious about our science ideas, and we make a grave mistake when we approach those people we want to help as if they're somehow just not very bright and that we have the answer. And it's just obvious if you look at the data. It's not obvious at all in many cases. There are other issues, of course, why people deny science, but I want to focus here on we have to come at this from a more humble attitude. And when we understand the history and philosophy of science, it can help us with our humility as we're trying to teach science more effectively. It overtly drives effective NOS instruction, overtly draws learners' attention to targeted NOS issues. And I'm going to give you some examples of this because to overtly draw their attention to what we want to teach them does not mean lecturing. You have to get people to think about things. So I've got two questions here I'd like to address or present to you that shows how you can ask highly educative questions that target ideas but still make people think. We know that people misunderstand what theories are. So note this question here. Note how it overtly lays out that the word theory in science is often wrongly interpreted by people as meaning guess, opinion, or a not well substantiated claim. The research is quite clear, by the way, that people think that if an idea is good enough, it'll become a law, and that theories, when enough data supports it, will become a law. So this straightforward says this is not an accurate notion. Notice how that would raise the learner's notion of, wait a second, I think that. What do you mean that's not right? And it's followed up with, how does that meaning not capture the confidence that scientists have in, and here you insert the theory that if you're a school teacher, a university faculty member, you have already helped students understand the power of that theory. And that's why I say this question is most effective when asked after students have been helped to understand the power of the theory in question. I recall doing this significantly with kinetic molecular theory. Here's another question that targets scientific theories. What prior knowledge did, and you insert the scientist, use in conceptualizing their research and analyzing the results? How does this illustrate that scientific theories guide researchers in determining what questions to ask, how to investigate those questions, and how to make sense of data? Note both these questions, and these are just two examples of many that can and should be asked when you're seeking to help people understand the nature of science, that target the NOS issue, but demands that people think about the issue that you're raising. We know effective NOS instruction occurs in a variety of contexts with extensive scaffolding. I've written before that a great way to begin is with Gestalt images and black box activities because they're great for introducing NOS ideas and issues, but without the overload, the cognitive overload of science content. We also need to address the nature of science in the context of laboratory experiences, inquiry or otherwise. For instance, when my students were doing laboratories that required them to inquire and to perhaps develop how they're going to investigate this or making sense of data, I raise questions such as, I want you to think about what you're doing here. How does this illustrate that you're having to make sense of the data and the data is not telling you what to think? How does your back and forth illustrate that you're not following a linear step-by-step scientific method? How does the work you're doing with others show the importance of collaboration science? These kinds of questions in the context of laboratory experiences can be quite powerful. When you do have to have your students or outreach efforts have people do a cookbook type activity, that's something that I'll do later in the year perhaps, but I'll raise the question So how does this distort how science really works? But we also need to draw attention to the NOS using historical and contemporary science examples. And in a paper I published in 2006, I argued, and the research is bearing this out, that this is quite important for resulting in authentic conceptual change. If you don't bring in actual historical and contemporary examples, students or those we work with in outreach efforts can deny what they're learning in their science classes, thinking that scientists, though, are a lot smarter than us. Scientists have technology and tools that we don't have here, and they can come up with all sorts of reasons to deny that what they're learning about the nature of science that is accurate, but somehow that's not how it is with real scientists. And so the historical and contemporary science examples are there to convince those who are trying to help understand the nature of science that this is how authentic science really works. We also have to raise NOS issues in the context of socio-scientific issues, not only to help them understand the importance of this NOS understanding, but also for them to make better informed socio-scientific decisions. Again, the NOS plays a role. It doesn't play the only role. There are many factors, emotional, value-laden, but the NOS does play a role, and research has made that quite clear. And then there has to be scaffolding between all these contexts. In a learning situation, students can get befuddled. And so sometimes, for example, if you're in the context of dealing with an authentic historical episode, you can look at, for example, Rutherford trying to make sense of the alpha particle bombardment and saying, how is this like what you were trying to do with your black box activity? How is it different? That scaffolding from one context to the other context and going the other way as well is very helpful for helping students make the sense we're trying to help them learn. And finally, effective NOS instruction requires that assessments accurately target desired NOS learning. Teachers are going to emphasize what is assessed on high-stakes tests. So any outreach efforts we might do, and I do a lot of them with teachers, we have to also consider that they assess this and that it plays a part in high-stakes exams. Moreover, as much as we'd like students to intrinsically just be interested in what we have to teach them, they will attend to what is assessed. We did when we were in school, and students today do the same thing. And we need both formative and summative assessments because, of course, what we learn about how students are piecing things together help us teach more effectively. And at the end, of course, we want to know what we have succeeded at and what we need to work more at, where students are still struggling to understand what we want them to understand about the nature of science. So we know a great deal. All the things I just mentioned there are well supported by research, and I look forward to talking more about this when we have our give and take session after you've watched this video and we meet on April 30th. But we haven't settled everything, and there are many things we need to work at to improve NOS instruction. One of the biggest disagreements exists regarding the framing of NOS learning outcomes. What are referred to as NOS tenets have guided science education, NOS instructional efforts for a number of decades. But they are increasingly being attacked for misrepresenting how science works. And I'm one of those people that originally was an advocate of NOS. I'll talk about the value of NOS tenets and why they have become so popular. But I long ago abandoned that approach and put forward the view of NOS questions rather than tenets. There's also what's referred to as the NOS family resemblance approach. And I just want to spend a little bit of time talking about both of these. NOS teaching and learning framed as tenets, I want to put in historical context. Norm Lennerman, who unfortunately recently passed away, put NOS teaching and learning at the foreground of science education efforts. He played a huge role in that. And he really moved forward attention to the NOS and understanding of effective NOS instruction. At the time that NOS tenets were put forward, times were different. What the public thought about science, they had misconceptions, and the NOS tenets were trying to address those. But I'm going to show you what the common NOS tenets are. And then I'm betting as I show you these, you're going to say, now, wait a minute, it's not that straightforward. One of them is they emphasize the distinction between observation and inference. The distinction between scientific laws and theories. I've mentioned the distinction, but I'm going to come back to how this is still too simplistic. They argue that scientific knowledge is empirically based. And notice it says based on or derived from observations of the natural world. Again, I want to come back to yes, but there are other things going on here. Scientific knowledge involves imagination and creativity. It's subjective, what they refer to as theory laden. Again, I'm going to point out that I have an issue with this. I'll come back to. I don't disagree that scientific knowledge has a subjective component, but I'll come back to why I have a problem with this. Science practice and scientific knowledge is embedded in and thus impacted by the wider culture. And finally, scientific knowledge is tentative and subject to change. This became so popular in science education circles that it became known as the Letterman 7 in one sense. And it not only framed the way people were thinking about NOS and science education efforts, it's the way NOS research was and still is to a large extent being conducted. In 2005, I started having a lot of concerns about NOS tenets. And I presented a paper at an international conference, the History and Philosophy of Science Teaching Conference, and it was later published. I've published a more updated version of this just this past year. And I've argued that we need to frame NOS teaching and learning as questions. I'm going to go through each of the NOS tenets to show you what I mean by that and give you some other examples. Notice that the notion that observation and inferences may be different is something worth addressing, but it's also worth addressing how an observation is an inference. Sense data, as you all know, does not come to us, and we're blank slates, and it has its meaning. A scientist looking at an X-ray crystallography picture is bringing a host of theoretical commitments to make sense of that. Our students look at the same picture and they don't see what we see. And so what we see, what we notice, what we make out of it is itself inference of some sort. And so this question addresses this in a more nuanced way. This NOS issue is important. It's worth addressing as questions. All right, scientific laws and theories are or do have some differences, but they're also related. And I want students to understand how they each guide research directions, methods, and analysis of data. Yes, scientific knowledge is connected to the natural world, but I want students to know in what ways it's based on reasons other than observational and experimental evidence. We know that a host of values and other factors come into play, from, again, Galileo taking a mathematical approach. Einstein did the same thing. Issues of Occam's razor, issues of coherence, theory of justification. A number of things come into play in determining how strongly we accept scientific knowledge. To what extent are science processes and ideas the product of human imagination and creativity? But importantly, what factors moderate imagination and creativity in the development and justification of science ideas? The fifth tenet turned into a question. Okay, yes, scientists certainly individually are quite subjective, and we can never get to, I would argue, total objectivity. We do, after all, think with our prior knowledge. But it's important to address with students to what extent can subjectivity be reduced or eliminated. There is a powerful role that public science plays in mitigating subjectivity. Scientific knowledge is culturally and socially embedded, but it transcends culture as well. And we know that because across the world, people are doing science. They're not doing Western science, and as if there's a Eastern science and a Northern science and a Southern science. They are doing what we refer to as science. That doesn't mean the West did not have a significant influence or the East had its influence as well. It means that we have to consider social and cultural embeddedness. Clearly, Darwin's ideas were influenced by his culture. We know that's the case, but we also have to address, particularly if we're going to help the public have trust in science, that it also transcends. And here I will argue is one of the most damaging NOS tenets, this notion that scientific knowledge is tentative. You and I know what we mean by that. The public does not. And so I want you to see how I've changed this into a question. And I foregrounded not science's tentativeness, but its durability. That well-established science knowledge is durable and enduring. And why is that the case? And yet, why is all science knowledge still potentially open to revision or even rejection? And then the crucial question, how is that possibility of revisiting and revising knowledge a strength of science? Notice how I've turned that tenet not only to a more nuanced set of questions, but pointing to the power of science. Then I also have a problem with Nos tenets, not just because I think they misrepresent the complexity of the history, nature of science, but they're quite limiting in what they do target. I think these sorts of issues are crucial, depending on the audience, depending on the grade level for school teachers. But these are things that are important, I think, to think about. And this is not an exhaustive list. This comes from a 2020 book chapter I wrote. How is it that we don't address science and religion as an important Nos issue? Because we know that religion is a huge impact on people's perception of the world, the natural world, let alone our society, and how they approach science. And people wrongly have a view that science and religion are at warfare. And as you all know, the history of science does not support the warfare thesis. Yes, there have been episodes of conflict, but complex interaction far better fits the history and nature of science. I've always enjoyed reading Peter Medawars' Is This Scientific Paper a Fraud? And of course, he's not talking about scientists cheating. He's talking about how scientific papers misrepresent how science really does work. If you look at the paper written by Watson and Crick that appeared in the journal Nature, and then you read Watson's account of their work on the double helix and other historical works on that historical episode, you're going to see how science really works. And what appears in journals is the sanitized version. And that makes sense. Why would scientists want to read about all the things that went on behind the scenes? But it's important that we help the public understand this, because think about ClimateGate. Anyone who understood the nature of science knew there was no smoking gun there. But to the public, that was a real scandal, because they saw what private science can look like. They just got a piece of it, and it did not fit their notions of what science how it should work, which is a sanitized version. The notion of a universal step-by-step scientific method. This is actually, even though it's not a tenet, it is something that is really addressed in Nos instructional efforts, trying to get students to understand that their scientists are not simply following a step-by-step method. But at the same time, it's not like anything goes. I understand Feyerabend's arguments, but it's not as if anything goes in most cases. And so we need to, again, deal with the nuanced issues that surround the notion of scientific methodologies, a pluralistic approach, depending on the question asked, insights, things like that. In what sense is scientific knowledge invented? In what sense is it discovered? The role of models, their strengths and limitations. Models are not just representations, they're also research tools. Again, there are other issues, but I want to give you a flavor of the importance of, at least what I think is, framing these Nos ideas as questions. Then there's the issue of the family resemblance approach, which I have a lot of respect for. And you'll see here that it really makes clear a number of things that go into how science works. I quite frankly think the issue of scientific questions or nature of science questions fits very well within this framework here. And so I have no problems with this. I just look at it as it sits here, and it needs a lot of unpacking. And I need to talk about unpacking because, to be very fair to those who advocate Nos tenets, they are not saying just teach those as those tenets are written. They will argue that those tenets need to be unpacked. But what I and many others are arguing, and have argued now for some time, is that teachers don't unpack them largely. And even science teacher educators don't unpack them because they themselves do not understand the nature of science deeply enough to unpack them. And so we have this problem of Nos tenets, even though they are meant to put forward ideas that we should address in Nos instructional efforts, and advocates will again maintain they should be unpacked. They don't promote the unpacking. I have put forward that the questions that I showed you, that I put forward in articles I've written, that those promote the unpacking, both with teachers and their students. Other NOS instructional issues. The obstacles to accurate NOS teaching and learning are profound. We would like to think that, well, of course everyone's behind this, but they are not. 25 years ago, more than 25 years ago, Lacken and Wellington wrote this. And this is as accurate today as it was when they wrote this in 1994. It just appears that it's the content. And for the scientists out there, I know you have a lot of science you have to teach in your classes. And therefore, attention to how science works is seen as taking away from the content you have to teach. And that's true from college all the way down to elementary school. Science education standards do mention the NOS, but outside of Project 2061, one of the finest reform documents I think has ever been written, they do so in a perfunctory and superficial manner. And they don't make a compelling case for how the history and nature of science matters for science education efforts and citizenship. Then we have the problem of high stakes examinations. And if they address the history and nature of science at all, oftentimes assess wrongly. Let me give you an example. I remember teaching high school in Wisconsin, and one of my students came in after having taken a required test, and so they weren't in my class the day before. And he says, "Hey, Mr. Clough, yesterday on the exam, they asked us about the step-by-step scientific method. I knew that was wrong, but I know what they wanted, so I picked the right answer." And that's what we have to deal with. And the importance is that if teachers see those kinds of things and know those kinds of things in our exams, they're going to teach to it. If they don't see anything about history and nature science, they're just not going to, most of them are not going to spend time accurately addressing this. High stakes tests have really taken us in the wrong direction, not because high stake tests couldn't be written well and take us in the right direction, but they just assess for things that not just in the history and nature of science, but science content. It's the lowest common denominator. If many of you saw what are on state tests and what teachers are teaching to, you would be appalled. And then there's the issue of, and we know this from research we've conducted following our graduates, because in the teacher education program I ran for 20 years at another university, we followed our graduates. I taught a course, and I still teach a course on the nature of science and science education. And we have all sorts of evidence that our students went out and actually did, and still do, seek to accurately portray the nature of science. And they get pushback from colleagues, administrators, even parents and students. Students will come along pretty quickly, parents after that, but colleagues and administrators, oftentimes, they don't see this as important. And I want you to think about this. We talked about the NOS misconceptions. Imagine you're a classroom teacher or you're doing outreach and you are working with this group. And if I'm a classroom teacher, the administrators have a lot of those nature of science misconceptions. My colleagues have a lot of those nature of science misconceptions. The students do, and their parents do. Who looks like the one with the misconceptions? And it's the one who's actually trying to accurately portray the nature of science. So we have a lot to do in our outreach efforts. And I've talked about teaching high school, teaching middle school. I've not taught elementary, but I know a lot of educators who are working with elementary teachers, trying to help them better teach about the nature of science. Those are outreach activities. For those of you who are philosophers and science and historians of science, scientists, we need to work together. That's why I've titled this Synergistic Opportunities, because we not only have to work on outreach to the public, we have to work to help teachers do better in schools. So together, we need to help promote and even perhaps foreground the practical relevance of the nature of science for science education citizenship. More personal and societal decision-making regarding socio-scientific issues. The public has to know why they can and must trust science. A trust that isn't blind, but follows from an understanding of how science truly works. We need assistance from philosophers of science and scientists to promote better teacher preparation and professional development that ensures teachers possess robust understanding of science content, history and nature of science, and pedagogy. We all need to understand how woefully low standards have become. Because there's a shortage of science teachers, they didn't do anything to bring more people in. They lowered the standards so anyone can teach anything. Right now in many states, if you have a primary area of license, say it's biology, you can teach chemistry with 6 credits of chemistry, physics with 6 credits of physics, earth science with 6 credits of earth science. And that's true with any discipline. If your major is physics, if you have 6 credits of biology, in many states, you can teach biology. And almost no program requires any attention to the history and philosophy of science. Now, I want to come back to why I mentioned I have 26 credits in the history and philosophy of science in my doctoral studies. I teach a course on the history and nature of science and science education. I speak authoritatively from my experience working with kids, teaching about the nature of science, working with the public, teaching about the history and nature of science. And the nuances that I raise with the NOS questions, I can address those. I will argue that many those in my field cannot. And their programs do not permit, the state, I should say, does not permit their programs to have a course in science education that would be devoted to the history and nature of science. So imagine working together, scientists, philosophers of science, and science educators on your campus to develop a course that is for not just prospective science teachers, but teachers out in the field. That is for all students that might apply to their general education requirements, that you help them better understand the history and nature of science. The science educator in those efforts can help with the pedagogy and the things we're trying to address in NOS instruction science classes. But they can also help their teachers then understand, their prospective teachers and experienced teachers, how do you effectively teach about the nature of science? But the philosophers of science and the scientists working with them, because most science educators have not taken any coursework in the history and philosophy of science. They have the tenets and they may have done some reading. And I find this to be a very large problem in our science education NOS efforts. Now, again, there are others like myself that if they don't have the coursework, they have read extensively. So I don't want to paint too broad of a picture, but this is a synergistic opportunity. And I would love to work with anyone who's interested to address this, because I am concerned about NOS tenets and the way it distorts the nature of science and how many science educators have adopted those tenets because they don't have the background. We all have to work together to collaboratively to provide compelling evidence supporting the contentions that NOS understanding does make a difference. We have initial evidence, but we need more evidence. It has to be compelling to policymakers, compelling to teachers, and I would even argue compelling to the public. I want to give you an example of a synergistic effort. This is a National Science Foundation project that I headed up, working with scientists and historian of science. Historian of science name is Matthew Stanley. He's at New York University right now. It's just been a pleasure working with him as well as with the scientists. I work with a scientist at Iowa State University in astronomy, biology, each of these areas. The COVID-19 education materials are recent. A colleague and I, Dr. Ben Herman, who has a dual appointment in science education and biology department at Texas A&M. This was his idea, and I was a co-PI on the project, but we developed COVID-19 education materials trying to assist with the COVID-19 pandemic education efforts. So working with all of these individuals, we have created stories, short historical science stories that accurately address how science ideas were developed, how there was disagreement about the meaning of the data, how scientists disagreed on a number of things, but how they came eventually, sometimes over long periods of time, to our current understanding. And I mentioned earlier that readings alone will not have much of a difference. So playing off what we know about effective pedagogy, and students' misconceptions. Each of these stories contains comments that overtly draw the reader's attention to the NOS issues in these stories. And there are also 4 questions. You might ask, why 4? Because the post-secondary science faculty said, we're not going to assign more than 4 questions. And so we said, all right, we'll stop at 4. So each of the stories has 4 questions that are educative. Just as the examples I provided earlier, they overtly draw the reader's attention to NOS ideas, accurate NOS ideas, in a way that makes them think about it. If you go to this site, and you'll see the URL here, I hope you will go to the site, we have 6 astronomy stories, 6 biology, 6 in physics, 6 in geology, 6 in chemistry. And we have, I think, 4 with the COVID-19 materials. Those stories were developed working with the scientists. They said, these are things we teach in introductory science courses. So we targeted those things. That there's a problem there, by the way, because when you look at these stories, you're going to say, these are all pretty much dead white guys, because the history of science is unfortunately a very sexist and racist history, reflecting that society was racist and sexist. And so I don't apologize for the stories we selected, because these are this is content that is taught in these areas, and we want the stories to be used. But my colleagues and I are looking to get additional funding to now broaden these stories to more accurately reflect contemporary science and better represent who does science. And so that's a very important effort we have underway. Another project that shows synergistic work with philosophers, historians, and science educators is understanding science. This is a one-stop shop. If when people ask me, where do I go for history, nature, or science resources if I'm a K through 12 teacher or even a university faculty member, I'll say, go to this site. This is the place you start. They make reference to the other project I just showed you that I headed up, but it just really is a really good source to begin with. And again, philosopher of science was involved in this, scientist. This just shows what can happen. These last 2 projects I've showed you show what happened when we work together. So for public outreach, we all love our own academic disciplines. I love science education. I love history, nature, science. My having 26 credit hours in history, nature, science, I always tell people, has pros and cons. The pros are, I'd like to think I understand it well enough to work with science education efforts to not distort the history, nature, science. But I have to always be aware that my love of the history and nature of science is not necessarily everyone else's love. And I have to keep in mind the developmental level of the audiences I'm targeting. And so I'm always worried that maybe I'm pressing too hard. I understand that history and nature of science is not the only end of science education. And I always remember that when I taught kids as well. We have many desired ends. So I love science education. I love history and nature of science. I know the philosophy of science faculty out there love their discipline. You scientists, you love your discipline. We like conveying it to our students, but we have to step back and ask, what are we really accomplishing? So again, that we love our disciplines has pros, it has cons. We love to foreground rational thinking. That's why we're academics. This has pros and cons. We'd like to think that we're all rational thinkers, but the research shows even we aren't, and the public certainly isn't. There are some books. This is just 3. There's many out there. There's a great deal of scholarship written about this. Thinking Fast and Slow, and one I'm working through right now. And what all of these, and again, much more scholarship points to, and this is Jonathan Haidt in his book, he points out that the human beings and the way we think are like a rider on an elephant. And the rider is the reason part of the brain. The elephant is the emotional side. And this is what research is showing in science education investigations into socio-scientific decision-making. Emotions and ideology play a huge role. My colleague, Dr. Ben Herman, who I work with on the COVID project, and we're working with now on another NSF project to develop more stories that address pseudoscience and how do we help students understand how to recognize pseudoscience for what it is. We have to start with that human beings are largely emotive reasoners. And I know it's hard to use emotion and reasoning in the same phrase, but I think that's the way we have to think about it. And we have to start where our target audience is, not where we are. Because what the research makes very clear is if you try to tell people how they're wrong, you're not going to be successful. We're not going to be successful in our public outreach efforts. We have to work together. The current science disinformation, the purposeful disinformation, distrust, and denial is placing all of us at risk. It's not good for society. It's not good for the well-being of the individuals who are adopting this distrust. And this last point, genuine and respectful collaborative efforts. That's not just between science educators, scientists, and philosophers of science. I'll be honest, in working with philosophers of science and scientists, not always, but I can feel at times that when you're a science educator, you're seen as lesser than those two fields. That's not a way that's going to work for our synergistic cooperation. I certainly don't look at philosophers of science or scientists as lesser. I love working with philosophers of science and scientists, and I do so extensively. We have to do that genuinely respecting what each of us brings to the table. And we have to take that same genuine, respectful, collaborative effort to the target audience. That's how we're going to combat this growing risk. So that's my presentation. I look very much forward to taking your questions and comments and discussing the ideas I've put forward in this presentation. I am, as you probably can see, passionate about this. I have experiences that I've not mentioned working with kids in the public schools. I know we can have a big impact, particularly if we work together. And again, I look forward to the interaction we'll have when the time comes. Thank you very much.